Welcome to this class. We'll be looking at NABTEB Physics past questions. Let's dive right into it. The first question here says, distinguish between electric conductors and insulators. Give 4 examples of each. Now, an electric conductor is a material or a substance that allows the free flow of charges or the free flow of electrons. So any material or any substance that allows the free flow of charges from one point of that material or substance to the other is called an electric conductor. So it allows the free flow of charges. An example of your electric conductors include all metals. So all metals are generally conductors of electricity. We also have substances such as salt solution, which we call brine, is also a free conductor. It's also a conductor of electricity. In fact, the human body is also a conductor of electricity. So current can pass through you. So if you touch current with your one hand and use the other hand to connect a wire, your current can flow through you, through the wire to the other end, but you might not survive it. Other examples of conductors include graphite. We also have carbon black. Carbon black is also a conductor, very good conductor of electricity. Now let's talk about insulators. Insulators are simply substances or any material that does not allow the flow of charge. The transfer of electron from one point of that material to the other is called an insulator. And insulators do not allow current to pass through them. Examples of your insulators include your plastic, your ceramic, your polythene bags, and etc. etc. So all of these that I just made mention of, anything that does not allow the flow of charges or the flow of electrons through them, they are called what? Insulators. So let's move on to the next question. The next question, question number 1b, says, what is a capacitor? Name 3 types of capacitor and 3 appliances that use capacitor for operation. Now, a capacitor is an apparatus that stores charges. Your capacitor stores charges. You can also say that a capacitor is an apparatus or an appliance that stores electricity, because charge is equal to electricity. So the amount of charge that is present in a body or an appliance is equal to the amount of electricity present in it. So if a capacitor stores charges, it also means that it stores what? Electricity. And we have different type of capacitor. We have what is called the variable air capacitor. Variable air capacitor. We have the paper capacitor. And we have the electrolytic capacitor. So these 3 types of capacitor are the types of capacitor that we have. So what are the 3 appliances that you can use your capacitor for? Now, one of the places where you can find your capacitor is your car ignition engine. In your car ignition engine, when you turn on the key starter of your car, what is prompting that car to start is the capacitor present in it. We also have it in your pumping machine. Capacitor is also present. In fact, even in your ceiling fan and your standing fans at home, a capacitor is also present. So all of these are appliances that make use of the capacitor. Moving on to the next question, which is question number 2. Question number 2a says, what is a p-n junction and how does it work? Now, a p-n junction is a point where the p semiconductor meets with your n semiconductor. And that point where your p semiconductor meets with your n semiconductor is called a p-n junction. And how does this p-n junction work? When the p semiconductor is connected to the positive terminal of your battery and the n semiconductor is connected to the negative terminal of the battery, there is low resistance to current flow and vice versa, which means that the resistance to current flow will be low when it is the p semiconductor is connected to the positive, and it will be high if it is the n semiconductor that is connected to the positive terminal of the battery. Moving on to the next question, it says distinguish between intrinsic and extrinsic semiconductors and give 2 examples of each. Now, when we're talking about the intrinsic semiconductor, we refer to them as the pure semiconductor. And why do we call them this pure semiconductor? They are the type of semiconductor that contain only one type of electron they only contain one type of electron. An example is your silicon semiconductor or your germanium semiconductor, and they are called what? Intrinsic semiconductors, because they only contain one type of electron present in that particular semiconductor. What about the extrinsic semiconductor? The extrinsic semiconductors are the type of semiconductors that contain many impurities, and in the process of adding these impurities to those semiconductors is what we call what? Doping. And this type of semiconductors, they are very different, and they are splitted into your P semiconductors and your N semiconductors. Both of them are called what? Extrinsic semiconductors. An example is your lead tellurium and your gallium arsenide. So your gallium arsenide and your lead tellurium, they are examples of your extrinsic semiconductors. Moving on to the next question, which is question number 3. It says, explain using kinetic molecular theory of matter why solid aluminum will change to liquid at 660 degrees Celsius without change in its temperature. Now, at 660 degrees Celsius, that is the melting point of aluminium. So at 660 degrees Celsius, any additional heat that is added to heating up that aluminium particle or aluminium metal is not going to increase the temperature, because all of that energy will be converted to latent heat of fusion of the aluminium. What do I mean? It means that all of the energy that is supplied to that particular aluminium particle at that particular time will be used up by the aluminium to melt it into its liquid state without a change in temperature, according to the latent heat of fusion of ice, latent heat of fusion of aluminium principle. And that is what? Following what? The principle of kinetic theory. So since it's following the kinetic theory principle, what it simply means that if I have 660 degrees Celsius of aluminium, that this 660 degrees Celsius of aluminium at this particular temperature here, aluminium is what has gotten to the highest amount of heat that it can contain at solid state. So at that point, any additional heat that is added to it is just to what? Melt the particles of that aluminium. And it will only increase in temperature when the aluminium is completely melted. So the change in the temperature is what going to remain constant, because there's not going to be any change in temperature at that particular time. So because there's no change in temperature at that particular time, this aluminium, any additional heat that is what added to it is just what completely melts all of the aluminium to its liquid state. So moving on to the next question, it says, explain why evaporation causes cooling and give the factors which affect its rate. Now, evaporation causes cooling because in evaporation, the most excited molecules of that particular liquid is what given off in evaporation. What do I mean? The molecules of a substance that carries the highest amount of energy is what is given off during evaporation. And in the process, because all of those molecules that have the highest amount of energy is given off, or the highest amount of heat is given off, then the remaining particles, the total kinetic energy present in the remaining molecules of that particular liquid, we have lesser amount of what? Energy, which means that the average kinetic energy of the molecules left after the evaporation has occurred, we have what? Less kinetic energy. And because the average kinetic energy has reduced, automatically it means that that particular liquid will become what? Cooler than when evaporation has not taken place. Okay, moving on to the next question, which is question number 4. AI says, state Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction simply states that the induced EMF of a circuit, that the induced EMF in a circuit is equal to the negative rate of change of the magnetic flux of that particular circuit. What does this mean? It's simply saying that the induced EMF is equal to minus d phi over dt. So this is what Faraday's law of electromagnetic induction is saying? It's saying that the induced EMF is equal to the negative rate of change of the magnetic flux. Question number 4AII says, state Lenz's law of electromagnetic induction. Lenz's law of electromagnetic induction simply states that the direction of the induced current is such that it opposes the change in the magnetic flux that produces it. What does this mean? This is the reason why your Faraday's law, the induced EMF there is always what? Negative. That it opposes the change in the magnetic flux. So the direction of the induced current always opposes the change in the what? Magnetic flux that would produce the induced EMF or the induced current. Moving on to the next question. It says, name two electrical devices whose operation is based on the laws of electromagnetic induction. And one of the devices whose operation is based on electromagnetic induction is your induction coil. Then we also have your electric generators. They use what? These laws of electromagnetic induction. Moving on to the next question, it says, explain with clearly labeled diagram how a transformer works. So look at this diagram. This is the diagram of a transformer. So this here is your transformer. So you can have your this is your magnetic core. Then you have your windings. So the primary windings are connected to your AC source. This is AC source. This is primary windings. Then you also have your secondary windings here. So this is your secondary windings. And this is your load. So whatever appliance you are connecting it to is called the load. So this is your AC source where the power is coming from. This is your primary windings and this is your secondary windings. And how does this work? The transformer has a formula that says that the number of windings, number of turns or windings in your secondary coil over the number of turns or windings in the primary coil is equals to the voltage in the secondary coil over the voltage in the primary coil. But please note that if in your transformer you discover that what your primary, when your secondary windings is greater than your primary windings, then this is a step up transformer. But when your secondary turns or your numbers of turns in the secondary is less than the numbers of turns in the primary, then it is what? A step down transformer. So this is what the diagram that what clearly explain, or a well-labeled diagram that explain how a transformer works, and this is the principle by which the transformer works. That's why you now have what two types of transformer, which is what the step-down transformer and the step-up transformer. To the next question, it says a 100-gram tennis ball. So we're given the mass of the ball as 100 grams. Was hit by a boy at a velocity. So we're given the initial velocity of the ball as 35 meters per second at a wall. It stopped on the wall for, so the time it takes to stop on the wall is 6 times 10 raised to the power minus 3 seconds before bouncing off at a velocity. So it bounces off from the wall at a velocity of 31 meters per second. What was the average force? The average force, we do not know. So now, because this ball bounces off from the wall, it means that the velocity with which it bounces will be what? Negative. So it bounces off with minus 31 meters per second. So the first thing we are going to do here is to what? Find the momentum of the ball. So the momentum of the ball, or you can say the change in momentum of the ball, this is equals to the mass of the ball times the change in velocity, which is final velocity minus initial velocity of the ball. And since this is what I have as 100 grams, this is the same thing as saying I have 100 over 1000, which will give me 1 over 10 kilogram. So this will give me 1 over 10 times, so I'll have minus 31 minus 35. So that's the same thing as saying I have 1 over 10 times minus 66, which will give me, if I divide this by 10, that will give me minus 6.6 kilogram meter per second. So this is the change in momentum. Now, since I've gotten the change in momentum of the ball, I'll have to find what? Average force. My average force is equals to change in momentum over change in time. So, and we know that my change in momentum is minus 6.6. So this is divided by my time, which is what? 6 times 10 raised to the power minus 3. So this is the same thing as saying I have minus 6.6 divided by 6 times 1 over 10 raised to the power minus 3. So this will give me 1 minus 1.1 times 10 raised to the power 3 Newton. So it means that the average force of this ball after it bounces off from the wall, because they said what was the average force? Average force the wall exerted on the ball. So this is the what? Average force that the wall exerted on the ball, because the wall was the one that pushed the ball with a what? A negative velocity, which is why I'm having my final velocity with which it pushes the ball as what? Minus 31 meter per second. So at the end of the day, the average force with which this ball moves off from this wall is going to be what? Minus 1.1 times 10 raised to the power 3 Newton. Moving on to the next question. Question number 5B. It says, explain what is meant by echo and discuss how it can be used to measure the velocity of sound in air and the speed of the depth of the ocean. Now, what is echo? Echo is simply the reflection of sound waves. So when sound travels through a distance and hit an obstacle, it bounces back. Hence, when you hear your echo, it always takes, if you produce a sound, for example, when I'm talking, if I'm talking in an empty room, after some time, I'm going to hear back myself talking again, because that sound has traveled to the end of the room and has what? Bounced back. It has reflected back to my what? Ears. Hence, I'm hearing it as what? An echo. So echo is simply what? Reflected sound. And it has what? Takes a period of time before what? You hear it back, and hence it is what? It can also be calculated. The distance it has traveled can be calculated. The speed of that sound can also be calculated. So with this echo, that is how your your ship, your submarines, and the others know the depth of the ocean because they use what? Ultrasound. So they send a sound downward, down to the bed of the ocean, and that sound will reverberate back to them as an echo, and then they can easily use that to calculate the depth of that particular ocean or that particular water body. So how do we do this? Now, the echo can be calculated. If you want to use it to calculate the velocity of sound in air, we know that what velocity ordinarily is supposed to give me distance or displacement over time. And I just explained that what for echo to happen, it has to travel to a particular distance to and fro. So let's say I make a sound at this point, and then this is the point where it hits. So if my sound travels down to this point and hit this particular substance and then move back, so I cannot hear it here as echo. So it has traveled a particular distance from here down to this place, and it has traveled from here down to this place again. That's distance. It means my total distance for my echo to be heard will be twice the original distance, which means that the velocity of sound in air will be equal to twice the distance, which is the distance of the echo divided by the time. So it means that my V is equal to 2D over T. So this is the formula you can use to calculate the velocity of sound in air. What about the depth of the ocean? Now we know that the depth of the ocean, which is the same as the height of the ocean, is the same thing as the distance of the distance that this particular sound we have to travel. And we already said that since my velocity is equal to twice the distance over time, because it was going to and fro, it simply means that I can easily calculate my distance also. If my distance is the same as depth, which is height, it means therefore that if V is equal to 2D over T, it also means that my V is equal to 2H over T. This means that I have my H, which is the depth here. H here is depth of the ocean, will be equal to velocity of sound times the time divided by 2. So it means that the depth of this ocean can be calculated using this formula that says velocity times time divided by 2. So this will become the formula to calculate the depth of the ocean using echo. Moving on to the next question. Question number 6. Explain what is meant by Doppler effect. Now, your Doppler effect is simply the apparent change in the frequency of a wave observed when there is relative motion between the observer and the source of the wave. So when there is a relative motion between the observer and the source of the wave, then what you have is Doppler effect. And you can easily calculate your Doppler effect by using your frequency, your observed frequency to be the frequency, open the bracket, then we have the velocity plus the velocity of plus or minus the velocity of the observer over the velocity plus the plus or minus the velocity of the source. So we use this formula here for calculating your Doppler effect. Like I said before, the Doppler effect is just talking about the differences, what you can observe, the change in the frequency that can be observed when both the source of a wave and the observer are in relative motion. So when the source of a wave and the observer of that particular wave are in relative motion, then there is a change in the frequency. So that change in the frequency is what we call Doppler effect. Moving on to the next question. Question number 7. 7A says the pole of a magnet is that portion of the magnet where its magnetic attraction appears to be strongest. Now, this statement is actually very true. What do I mean? In a magnet, the pole is where you have the strongest magnetic attraction. So if I have a bar magnet, for example, if this is a bar magnet, and I have my north pole and my south pole this way, this magnet, the magnetic field is created this way. So I have my magnetic field this way. So looking at this magnetic field, if I put an object closer to this pole, which is the north pole here, you discover that what it will be easily magnetized compared to when I put the object here. So closer to any one of the pole, either the north pole or the south pole, that is when we have the strongest magnetic property of a magnet. At the poles is where the magnetic properties are concentrated. So we have more of their magnetic properties at the poles. So at the poles, we have what? A greater portion of this what? Magnetic attraction. So the pole of a magnet is that portion of the magnet where the magnetic attraction appears to be the strongest. That is where you have the highest concentration of their magnetic strength. Then next question says, distinguish between scalar field and vector field and give two examples of each. Now, a scalar field is a type of field where the particular quantity or the variable that we're talking about here only has what? Magnitude. It's a type of field where the quantity has only magnitude but has no direction. An example is temperature field. So if you have a temperature field, it only has what? Magnitude and has no direction. Another example is when you're talking about something like a mass field. So if you have a mass field, it's also having what? Only what? Magnitude, but no direction. While your vector field is a type of field that has both magnitude and direction. Example is your magnetic field. Your magnetic field is a vector field because it has both magnitude and direction. Like I was showing here, if in this particular what field here that is created, you always have what? In a magnet, the field that is created is always what? From the north pole down to the what? South pole. So that's what? The direction. And it has what? Magnitude in terms of what? Value. We also have other vector field like your electric field or your electrostatic field or your gravitational field as well. They are all what? They are all vector fields. Moving on to the next question, question number 8. It says, explain what is meant by a field. Now, a field is a region or space where the effect of a force can be felt. A region or space where the effect of a force can be felt. This force may be gravitational, may be magnetic, may be electromagnetic, etc. So the region or space where the effect of a force can be felt is called a field. So a field does not necessarily mean a football field. It can be an electric field. So a field in physics is not a football field. It is what? A region or space where the effect of a force can be felt. So question number 8b says, mention 3 types of fields known to you. Examples of the types of field that we have what is called the magnetic field, we have electromagnetic field, we have the gravitational field, we have the electric or the electrostatic field. So all of these are the types of field that we know. With this, we've come to the end of today's class, and I believe you had a nice time with us in this tutorial. Don't forget to go to our channel for more videos just like this as we have done before. Thank you.
Hi, I'm sure you enjoyed the content you just watched. To see more episodes as that, preparing you for your oncoming exams, smash the subscribe button on this channel right now and visit the playlist that we've made for you, covering over 50 types of different exams, including JAMB, WAEC, Kakao, NET, IALT, and the likes like that.